Welcome to another test and teardown video. Look at this beauty. Another HP. Oh my god, I love it every time I get an HP. This one is a model 616B UHF Signal Generator. So this thing can do kilomegacycles. Well, also known as gigahertz, all right? So this thing can generate from 1.8 to 4.2 gigahertz. Oh, that is amazing. I can't wait to test this thing. I don't understand this dial, by the way. Look at the scale from 0 and then it goes around, right? The funny thing is the ratio from this knob to the readout doesn't add up. So when I turn this to the next full gigahertz here, it's not lining up. See, here's a little bit too little, right? And then I go to 1. Ooh. See, now it's 20 something, right? And then let's take the next one. Ooh, it's 15. And then it's 10. And then it's what? I don't know. What do you think about that? Isn't that just weird? Maybe it's just me that's picky. I think you need to measure the frequency externally, but back in 1950, I think this is from 1950, it wasn't that easy to measure the gigahertz. You needed to mix it down, and with something else you really needed to know that frequency, and then I don't know, got some really sexy output attenuator. So there's one that sweeps what, 15 dB, and then there's another one that goes around here. And the power measurement and feedback system for power, that is made with a bolometer. So that means a temperature sensor, and of course a reference temperature and all that stuff. So that is really nice because it's super accurate over a broad frequency range. So that is of course how they made that. Got some different kinds of modulation, AM, no AM, FM. And then it can do some FM here. I haven't figured out exactly how this pulse width, delay and rates is working. That is something we need to look at when we get this baby up and running. Got some sync, plus minus AC. What is that thingy? This is a power indicator, and I assume it is connected with this. I don't know exactly yet. Oh, and this model is with a power cable out in the front. That is a little bit annoying. There's another model with a connector in the front, but I think there is a good explanation for this, because this is just how this unit is built. You just unscrew those screws here in the front and then pull out everything in one unit from the shield. And obviously you want the mains cable to be in the front. You could have had a connector in the back. I really don't like the design with a cable out in the front, but that was 1940-50 kind of style. So it is still here, of course, because it is that old. And we got some different inputs and outputs for modulation. I am also a little bit curious if this works, how much is working here or not. It is a 30 kilo unit. So that is why we got those big, hefty handles. So now I'm gonna try and lift it up on the table and connect a spectrum analyzer, and hopefully we're gonna see some gigahertz. That could be cool. I think we are ready to power up this thing. Let's turn on the spectrum analyzer so we can see if there's any output. I checked the manual and it says 160 watts. this is very useful information because I'm always verifying power usage when I boot up stuff like this for the first time. Also, I found a very cool note here on the top. So it says it was checked for accuracy and it's all up to specs, all functions, and look at that. It was tested in 1972. So, and this is actually an original form with a number and everything on it, and this is a form is from 1964. That's pretty cool, huh? And this is kept here original, and the unit is really in mint condition. That is great. No nasty stuff on it. So are we ready to power it up? Let me see. That is mains and no power usage. 130 watts back to 100. 70 watts. That's it. So that can't be. And it's 80 watts now, 90 watts, 100. Ooh. Then we got output 120. Of course, this thing is full of tubes, so it's got its own life. Output 118, and it's stable. Ooh, wow! Ooh. What you can't see is how beautiful this is lit. Damn, my camera is not recording this, but it is deep red, beautiful. All right, so let's connect. Yes, there is a spike, and this is a 2 gigahertz. See, I'm at 2 gigahertz. Let's crank it up and see. Haha, it goes up. Let me play with the output. Oh, that is the other way. Oh, look at that, and it goes all the way up. Yay, 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 and aha. This is something that I didn't really understand how this works. But this is the power set. This is how it works. So you adjust this for 0. Now you know the attenuation is correct for this frequency. This is what you need to do manually. So then you can change the frequencies and then yeah, exactly. So, oh, did you hear that? Click. Some funky stuff is happening in there. Let's crank it all the way up to 3 gigahertz. So let's see how accurate can we do this now. This is exactly 3. And we're here. So start 2.8 and then the stop is 3.2. Let's take a marker. Just a peak. So 3 and then 2 zeros. Are you kidding me? And all I did was just to adjust this thing. Holy cannoli, that is amazing. So let's try again with 3.1, and I'm only looking at this scale. See, don't you think this is in the middle? Yeah. Okay, let's hit peak again. 3.1. Oh my gosh, this thing is accurate. 3.2 and it goes 3.2. Yeah. Wow. This thing truly works. So, of course, I'm gonna put this for 3 again, peak, and then I'm gonna play a little bit with the different features, the modulations, the pulses, and stuff like that. And then we're gonna see a little bit on how everything works. This is cool. I'm having a lot of fun testing this unit. Look what I'm doing here. I have a normal oscilloscope. That is, of course, a time domain, right? And I'm looking at the sync output. This is actually the modulation, right? So what I'm doing is this modulation, this is the internal modulation, and I'm using this internal pulse generator here. and see if I change the rate, that is how many pulses that per millisecond and all that stuff. Look at the spectrum analyzer and the scope, and they're measuring exactly the same thing. So if I measure, see, this is now 5 milliseconds per division, more or less, and see, this is also 5 milliseconds per time, because now I'm in time, because I'm in zero span mode. And I think instead of running free run, of course I can go on a video trigger, put a trigger here, and because I am at a single frequency, and that is 3 gigahertz, and this is my bandwidth, and yeah, 0 hertz, so that means this is now time, because I'm looking at 3 gigahertz, and then it's actually demodulating and showing the depth of modulation in time. So I've just set the sweep for 50 milliseconds, and that means I got 55 milliseconds per division, and now it's more or less like a scope. So that's pretty cool. Let's try some other thing and put it into FM. So now I'm in FM, and then I can crank up the FM modulation. See, if I crank up the modulation, it looks a little bit like this. And all I have to do is change the bass frequency a little bit. See, now it's getting closer to a sine. And this is because my frequency modulation is now going in and out of the spectrum analyzer's bandwidth filter, right? So this is what we see here. And if I crank down the modulation, so I get less and less and less and less. Zero modulation. Oh, I need to go to free run. And then I can fine adjust the frequency. So this is my peak power, and then it goes lower to each side of my bandwidth filter. But anyway, this is just how I measure stuff. This unit is just working. Everything is working, and I'm super happy about how accurate it is. I also figured out how to use the power calibration here to calibrate the attenuator. What you do is you look at the meter here, and then you dial for 0. See, you want this to measure or to show 0 on the attenuator, and then you crank the drive up and down of this resonant driver system that is in here. And now the normal attenuator is now working. Now you can, if you look here, of course I didn't calibrate my setup here with this ridiculous cable here is full of loss, and also I put in a 10 dB attenuator here because I was afraid, what if the output attenuator in this unit was defect, then I could get a lot of watts out of this one, and I really want to just blow up my tiny little attenuator here if something is wrong with a unit like this, because there's the internal oscillator in this one is tube based and all sorts of nasty stuff, so it could potentially deliver quite a lot of power if something was wrong in the output system here. So always think about that. But then this is calibrated fine, and then I can go, see, I'm at -10 for 0, no, more or less. Yeah, no, I was here. And then I can go 10, 20, 40, 50. I can just go all the way down, right? So there's a super nice variable attenuator. Let me show you guys this. That is sexy. I love it. All the way to -1,000,000 gazillion. 125. Who can hear that? This is way below the detection level of this analyzer. You need one of the more expensive ones to be able to detect the last bits here. That's for sure. So I've been playing a little bit with settings on my spectrum analyzer, bandwidth, attenuation, preamp, and all that. And now this is a -100 dBm signal, and I'm more or less able to catch it. I'm also running with averages and stuff like that, so this is why it's moving a little bit. That is because I'm hitting the frequency bins and the resolution of everything now. I'm pushing the limit of what I can detect with this analyzer. And as you can see, I still got like 10 dB more to go. See, this is minus 100, and let's try and 110. Let's see if I can. Ooh, it's difficult to detect, but it is definitely there. So let's not touch this one because this is the calibration. And let's go back to, what is that? 60 is here, right? And then it's going all the way up again. So it's a lot of fun playing with this unit. I think it is time to see what is inside, right? Let's open. This is inside the case. They've even closed all the air circulation holes with a really fine grit, and this is welded to the case at very short distance. This is of course to isolate all sorts of RF radiation. Look, there's even a shield sock all the way around here, so to make good electrical contact all the way around the case, so that is really good quality. And this is the bottom part of the unit where all the back sides of all the tube sockets and all the wiring can be seen, and it's really beautiful made. See all the wires. I just love this kind of hand work. Of course it took a long time to wire all this up, but I guess they made really good documentation. Got all the big capacitors there like that. And here we got all the high voltage capacitors and filter resistors. I powered this up for a few hours today and had a lot of cool experiments with it, and now it's a few hours ago I left it to discharge everything, and also I measured voltage on all those. See, we see a lot of really big capacitors all over the place, and I measured 0 volts on everything. So now I can play around inside here and it's still going to be safe. Oh, we got quite a lot of voltage regulator tubes. See, those are easy to identify. Oh, and here on the side, danger high voltage 840. Oi. That is the side of all the fun parts. Whoa, look at that stuff. We're going to investigate a little bit more in detail here what we got. I think we need some more light. Yeah, look at that, baby. So this is the cavity. Look at that meter. How nice. They completely sealed everything, and that is feed through filters. Oh, look at that knob. Isn't that cute? Wow. Yeah. That's pretty cool. And that will be, let me see. Yes, this is definitely the attenuator part. And it is connected to this one. Let me see if I can get access. Oh, it's difficult to get in here. Yeah, here we go. See, this moves the coupling to the temperature probe, and this is the calibration temperature probe you move in and out, and I guess this is a feed-through capacitor for the temperature sensor that is at this end, and it goes into the cavity here. And this is the oscillator tube, and it's right in here. So this is the coupling for the sense power, and where it's regulating how much drive we're feeding into the main tube. And the other end, what we see down here, that is the output coupler. That is a variable coupler, and you move this in and out of the cavity, and this way you have a very, very well defined coupling. And this is of course why you can make such a good attenuator for this kind of high frequencies. And this part is the output coupler, and this coax cable you can see here at the end of the output coupler. All it does is go straight to the output connector. What is that? That is a funny way of holding that wire. Why is that necessary? But anyway, let's try and dial. See? This is the geared function of the attenuator. And here we can see how this coupler is moving a lot all the way out here. So this is minus 125 dB, and then I go all the way in here, and now we got 0 dBm. That is so cool. It is really beautiful. I of course want to have a look in here. I think there's only one little screw here. And we're definitely gonna look in there and see if we can find some cool stuff. Oh yeah, look what I also found. This is the here we go. This is the frequency dial. And the frequency dial is also connected with a very big potmeter, this big black one here. And of course the electronics also needs to know the different frequencies, because at different frequencies they need to compensate for a lot of stuff. And this way there will be some different compensation for level, modulation index, and how much energy to feed into everything when you are modulating and all that kind of stuff. So it's accurate all the way around. So this is done mechanically. Well, beautiful potmeter, that one. 100K. And again, that will be all the modulation, input, output goes in nice coax all the way up here to everything. Oh, we got a lot of that will be voltage regulator tubes. They're normally looking like that, isn't it? Yep, exactly what it is. That's easy to see when there's only 2 wires to each tube. So that will be voltage regulator tubes, and they're probably connected in series, half of them, so it can be able to regulate at much higher voltage. And you can even see here it is voltage regulator tubes. That is easy to see here, right? So yeah, a beautiful unit. And what is in here? 1800 megacycles, 2800 megacycles. What is in there? That is they just want to say what those 2 pots are doing. This is actually the mains input filter, and this will be the mains transformator, voltage wiring something here, I guess. Why else would this be accessible like that, right? But I think we should have a look in here, and this is really, really beautiful. I did read a little bit in the manual about how to disassemble this and how to open this, and it's actually needed, because I don't want to break this. I really want to keep it as it is, because it's really, really sexy the way it is. So this is the socket around this. Look how well this is isolated, and that is definitely feed through capacitors, and a little socket for the oscillator tube. Wow. Oh, here we go. This is the business end. I got the tube. And I think the way you take it out is to release this mechanism here at the end. I don't know if I will be able to do that without breaking it, but there's definitely going to be a way to do that. And then this piece of metal can pull out this way, and then the tube can be pulled out backward. So here is something I want to show you. The ring, the golden ring, is actually the grid, right? And that grid is, as you can see, coupled via this long ring all the way back into the cavity, so it's folded like that. And this is, of course, the feedback resonance. Okay, so this is what's driving the resonance. Let's see this little pin that sticks out here in the right side. That is the temperature sensor. See, if I turn this, can you see now the pin is going in? So that is actually the bolometer, is it called? This is how to calibrate the RF level inside the cavity. And the left side here is actually the coupler. Well, let me remove this little wire. So look at the, let's see if I can turn there. See, this is the attenuator. So now I'm attenuating, and this is full output power. Can you see there's a tiny little loop down there? This is actually the pickup signal coil from the cavity. And the distance here, because this is inside a little tube that goes all this way, all the way back here, right? So the further you go away, and this is linear, right? So this is just genius. And this is, of course, why this attenuator is always working, and it is impossible to break. Let me try and dial the frequency. See what happens. Let me go. This is, of course, up in frequency. This is the highest frequency. Then the cavity is shortest. So, and if I go up, make it longer and longer and longer, frequency goes down, 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 down. And then this is how it works. And it goes, of course, all the way back to 1.8 gigahertz. And it is just beautiful, the mechanical construction here. See, it was possible to lift up the two locking rings. We've got two of them. And now look what happens. This little ring here can be lifted up. Oh, I need 2 fingers. So I was able to figure this out. So after releasing the two locking mechanisms and also this screw. The fun thing is there's only one of those set screws. And look at that. See those 2 marks? That must be the original mounting. So there were actually 2 screws, right? So one is lost. So when I turn this around, ooh, 2 marks again. And not a mark down here. And then there's another mark down here. And this is where it was when I pulled it apart, right? So somebody have been in here before me, or this is not the original tube. But it's a beautiful tube. It's amazing. This one runs up to 4.2 gigahertz. Wow. Look at that beautiful tube. And it goes in from the bottom here and connects to this. Is super heavy, this piece, by the way. You can see how thick and solid it is. Really well made mechanics. This is a view into the beast from the bottom. Here is the frequency dial. And this is of course the frequency readout, this big one, and it is connected to the big wheel. And look, there's a micro switch connected with an arm to this big wheel. I don't know if we can get a better view. Yes, we can. Look at that. So when I dial the frequency, it's going to change the micro switch, and this happens at 2.65 gigahertz. Then the electronics knows this is the exact point of switch over. And look at this. Yeah, this is the pot meter I talked about earlier. At the end of the frequency dial, we got two wheels, and look, one of them is a tiny little bit bigger or smaller than the other one. And then look at the black one. Got a little, see, a little knot here in the low end, and then it reaches, see, the stop will touch this one, right, when we are at maximum, and then the other one is gonna touch, see, this is a low one, and this, yeah, they're gonna touch the stop. So we have two of them, right? So that is how it is handled when you reach the very end. And that was all the voltage regulation tubes that I talked about. Oh, this one is a little bit loose. Yeah, this is probably just the way it is. I really like the shielded capacitors. We also got a lot of very big capacitors in here as well for all this high voltage stuff. I removed this funny tie-up wire stuff here. That was definitely not original. And this wire is supposed to be able to move freely. And this is the other end of the cavity, and this is of course the anode connection. And I think we can unscrew this and just take out this connection. There will be a coax connection all the way to the anode, but I guess there's no need to poke any of this stuff to pieces. There's probably a tube with some sliders in there, and we don't want to ruin the calibrations or anything. Well, I guess that we could expect a lot of high voltage on this one, right? Look at that. Ooh, we better clean that. Oh, so I've been playing a little bit with the fine-tuning of the frequency settings. As you can see here, we are about 3 gigahertz, and this is also about 3 gigahertz. And the reason why I say this is because after I pulled everything together and put it back again, it was just like a quarter of a millimeter off, and that I couldn't have. So what I did is I looked in the manual about how to adjust the frequency, and it's this bolt right here in the middle of the picture now. This set screw, we got two of them by the way, and they need to be loosened, and then you put in your hex key in this hole, and then you can actually hold the cavity from a movement, and then you can force dial this into the correct setting and double check again back and forward a few times, and then you can tighten the set screws, and now it's super accurate. So this is exactly how they do this, just a simple manual offset. Alright, also I wanted to show you guys what we got here on the top of the cavity. And what do you think that is? Temperature sensing devices and power heaters and some resistors for, I don't know exactly what that is. Maybe we can see in the schematics. But the thing is, they're heating up the entire cavity, and this way controlling and fixing the frequency alignments. And I've been measuring this over a couple of hours, and it is insanely accurate and stable. The drift is very, very small. Man, this is amazing what they've done here. So they have just found the exact perfect relationship between temperature regulation and how this whole mechanical thing changes its parameters. They're just geniuses, those guys.